During the summer of 1973, 3 astronauts, Alan Bean, Jack Lausma, and Dr. Owen Garriott, were launched into space, where they spent almost 2 months in the Skylab spacecraft, the world's first laboratory in space. The crew performed a variety of scientific experiments and demonstrations. The onboard scientist, officially designated a scientist pilot, was Dr. Owen Garriott, a former professor of electrical engineering and an astronaut since 1965. During the mission, Dr. Garriott conducted a number of demonstrations specifically for the use of science students. Back on Earth, Dr. Garriott discusses some of his Skylab experiences with high school students.
Skylab is perhaps the most unusual laboratory that you can imagine. Living in weightlessness meant that you didn't walk from point A to point B. Instead, you floated. And to do that, you simply pushed yourself off and drifted over to the spot that you were headed for. Now here you see some of our weightless gyrations that we went through during a little time we took away from our work schedule. Now this weightlessness also made it possible for us to conduct some science demonstrations that we simply couldn't do here on Earth because of the strong influence of gravity. Now one of our demonstrations involved the Earth's magnetic field, and this completely surrounds the Earth, making in effect the Earth itself a giant magnet. One of the many things that this field does is to protect us from dangerous solar particle radiation coming not only from the sun but also from the outer reaches of our galaxy. Skylab moves through the steady magnetic field of the Earth, making almost 16 revolutions every 24 hours. As you see, Skylab's orientation with respect to the nearby magnetic field is constantly changing. The uniqueness of the Earth's magnetic field has led some to the conclusion that this field may have been a vital factor even in the development of life here on Earth. We also know that even minute changes in the Earth's magnetic field, both its strength and in its direction, can seriously interfere with some aircraft instruments and also ships' compasses. And this can lead to endangering lives when their navigation is performed by reference to the strength and direction of the Earth's magnetic field. This field also is basically related to the appearance of aurora, or northern and southern lights as we call them, and interacts with the solar wind also, which is a new discovery of our space age. Let's take a look at some of our TV footage and see a Skylab demonstration in which some of the effects of the Earth's magnetic field are demonstrated.
I'm sure most all of you, at least at one time or another in your past, have had the occasion to use a compass. It's of course made from just a little magnet, and the north end always points toward the North Pole, and you can use it to determine, for example, your way out of the woods or your way on a hike and that sort of thing. Well, perhaps many of you haven't ever thought about whether or not the Earth's field extends far out into space. For example, here we are up in Skylab, some 270 miles above the surface of the Earth, and indeed the Earth's magnetic field does extend out this far, and in fact a good deal further. But we can demonstrate that as well, and perhaps you would enjoy seeing such a demonstration. Here's a group of little magnets that I have. These are about 2 inches long and about 2/10 of an inch in diameter. And when we put these just floating out in midair, like I'm doing here, you can see that they take on a very definite orientation. For example, there is one. I've released it right out in the center now, and you can see it is settling down to a specific orientation. That's the direction in which the Earth's magnetic field is running here, right along parallel to this little bar magnet. And we can, of course, use this to determine the direction of the Earth's field right up here at the location Skylab is at. Now, as we travel around the Earth, if we could watch this for a longer period, we would see this little magnet make several rotations as we circle the Earth, because the direction of the Earth's magnetic field is changing. Now, here's another thing that we can do. You see, we must not get too close to it with another magnet, because when we do, the two of them interact, and they very much perturb and influence the other one. Now, let me just make a couple other little demonstrations here for you. First of all, we found, you see, that one magnet aligns very nicely with the Earth's field. And if you watch very carefully, you can see this dipole oscillate back and forth. And I'm removing all the other magnets so that they do not influence it. Now, perhaps you'd find interesting in one of your science classes to try to compute the period of that little compass. Or another way to do it, you can measure the period from this oscillation and compute the strength of the Earth's magnetic field right up here at the Skylab orbit. To do it, you'll need to know a little bit about this magnet, but you can estimate that approximately from the fact that it's a 2-inch long, 2-inch diameter magnet, and make a calculation to determine what the period of that oscillation should be. Now, here's another little question that might be appropriate for some of the younger members of our audience. Suppose I take 2 of these magnets and I put them together like this. Now, if I put these out here and let them float, you see, they have almost no tendency at all to line up with the Earth's field. There's just a little bit remaining, but almost no tendency at all. And so perhaps you can explain that, or if you can't, you can ask your science teacher, and he or she can tell you why it is with 2 magnets like this, we seem to lose that tendency to line up with the Earth's field. Well, we saw the period of one oscillation a minute ago. Let me try it with 2 magnets, end to end like this. Now you see, they also oscillate. It's not like the 2 side by side. 2 end to end will still oscillate. And maybe you can see that. And you can measure this period. And from that period, you can again calculate the Earth's field, or you can determine something about the inertias of these combination of 2 magnets. And I'll leave that for another calculation for your science class. Now we'll give you a close-up look at the oscillation of one magnet. Put it back in the center. And now we'll use 2 to oscillate. And you see the period of this oscillation is a good deal more slow when we have 2 of them together. And we can extend that even to 3 rods if we like. And there the period is very clear and can be measured rather accurately. Now if I put 3 side by side, we again see they'll have a different period. And they move a little too fast there. There we go.
Before resuming our Skylab demonstrations, I'd like to give you an opportunity to measure the period of the oscillations of the different combinations of magnets that we've just been looking at. Now, after you've measured these periods and the film is ended, your instructor will supply you with the other data that are needed to calculate either the moment of inertia or the strength of the Earth's magnetic field from our Skylab location up in space. Now, here's how I would suggest that you make the measurement of the period of these oscillations. Now, this little pin that I'm going to show you here will represent the dipole that you've just seen, and in my other hand, I've got a stopwatch. And so the way I would measure that period is to wait until the dipole has tipped to one extreme, its motion, and more or less stopped, ready to turn around, and at that point, start your stopwatch. And then measure at least 1, or if there is time, perhaps 2, or even 3 oscillations of the dipole, and then stop the stopwatch. Now, I've just simulated there, for example, measuring 3 of the oscillations, and my stopwatch reads 10.5 seconds. And so the period, dividing 10.5 by 3, gives us 3.5 seconds per oscillation of the dipole. And then you'll want to go back, of course, and measure that period for each of the various combinations of magnets that we've just been looking at. First, let's make a dry run. Start your stopwatch precisely when you see the dot and hear the tone. Count the oscillations. 1, 2, and then stop the watch when you see the dot again and hear the tone. Okay? Now we're going to repeat the footage for the single magnet so you can make that measurement. When you're through, write down the measurement on your paper, and then we can measure the period of the oscillations for 2 magnets. Now let's measure the period of 3 magnets side by side and write that number down. Then finally, we'll measure the period of the 3 magnets when they're placed end to end in a long single dipole. When you've completed that, we'll have 4 measurements recorded on our paper, and we'll use these measurements in our calculations when the film is ended. Now, in another demonstration, we will observe the effect of a magnet attached to a nut, similar to this one, that we caused to spin like a top in space. Now we're going to tape a little magnet to the nut, just like this. Use a little piece of gray tape, just the way we did on board the spacecraft. And we're going to observe the effect of this magnet on the spinning of the nut. Note that the polarity of this flat magnet is not along its long axis as it is with the little bar magnets. Instead, the north and south poles are located on the flat sides. What we'll see is, first of all, when we launch it in an orientation parallel to the Earth's magnetic field, that the spin is fairly stable.
You see, once again, it continues to spin pretty nearly stably about the direction in which it was launched.
But what happens if we allow the nut and the magnet to float freely in space? Let's take a look at the case in which the attached magnet has an orientation or a polarity in which its dipole is not in the same direction as that of the Earth's magnetic field.
But the next thing I want to show is when I tip these in a direction perpendicular to that. If it's not spinning, watch what it does. You see, it tips right over and turns parallel to the Earth's field so that its spin axis, or its axis through the disk, is oriented with the Earth's field just the way it was before. That's its normal tendency, is to tip right over and align its own dipole with the direction of the Earth's field. Now I'm going to spin it about this direction, and we'll see what its reaction is. All right, now it's more or less spin axis perpendicular to the Earth's field at this point. Well, we have to watch it for just a minute here, but the thing that I want you to observe is the fact that its spin axis is tipping over in another direction. You see how it's now tipped over to the point where it's almost facing the camera. And now it has. It's tipped about 90 degrees, but not toward the Earth's field, which is off to my right. Instead, it is tipped over towards the camera. Now, this is called precession. Now we'll go back and check the Earth's field once more and see whether or not it's changed. Take another of our little magnets. And it may have changed a little bit, but not a great deal in the time that we've been talking. But these magnets are already influencing each other, as you can see. And they'll align themselves just like that in the direction of the Earth's field.
Now this concludes our demonstrations of magnetic effects in space. We've observed, first of all, the oscillations of various combinations of little bar magnets. And then next we've seen the precession of a spinning object, in this case a small gyroscope represented by this spinning nut with a magnet attached. After you've completed the suggested calculations, you will know that the Earth's magnetic field extends far out into space above the Earth, and you will have calculated its magnitude and observed its changing direction. We've also seen the very first demonstration of precession ever observed in this marvelous new laboratory that we call space. And in this laboratory, of course, gravitational forces no longer perturb our experiments. Perhaps your own curiosity and imagination will suggest even more sophisticated experiments to you, which can be demonstrated on later flights.